Thank you, Professor Rosenfeld. Yes, indeed, it's my great pleasure and honor to introduce to all of us, especially graduate students, our speaker, colloquium speaker today, Dr. Edward W. Kolb. As we heard, I have known Dr. Kolb for a long time, more than half a century. One thing I will mention is I still remember that hot air, big engine sound, and smoke of oil from his British sports car that would ride in summer New Orleans. Anyway, one thing, fellas, hardly a handful of people in the history of mankind has the privilege and the genius to create a new science. And Dr. Kolb is one of the co-founders of the whole subject of particle astrophysics or astroparticle physics. As he would say, I'm copying or paraphrasing some phrases I heard from him. From the Big Bang, we know the energies were so great that cosmology must involve particles. Okay. On the other hand, knowledge of particle tells you if that is the case, that Big Bang, the beginning of the cosmology or the cosmos as we know today. If we have to accept that, then we have to bring cosmology to particles and particles to cosmology. And he is one of the first directors at the Fermilab of astroparticle physics. Okay. Since then, he has been director of the Kavli Institute at Chicago. He claims that because people discovered his genius in organization so early on in his career, he had been chairman of the astrophysics and astronomy department in Chicago, and dean of physical sciences. In point of fact, in one of the American Center of Physics March meeting organizations, I was there, and I somehow mentioned, oh, where are you from? Somebody said, from Chicago. I said, oh, I know Rocky Kolb. Oh, he's our dean. Okay. Anyway, he's done a lot of important things and has been recognized for those. So I'm going to read a few things of those. Prize winner. Let's hold the whole list. In 2024, Leonfield Prize of the American Physical Society. In 2010, Danny Heinemann Prize of the American Institute of Physics, AIP. Then in 2003, Orsted Medal of the AAPT, American Association for Physics Teachers. He has more. I don't want to read the whole thing because Schrödinger is waiting. Schrödinger. Okay, good. He has published more than 200 refereed publications. He has co-authored, I think, 2 books, or at least 1 book, Early Universe, which is standard textbook in particle physics and cosmology. His book for the general public, Blind Watchers of the Sky, it reminds me of myself, received in 1996 Emmy Award for of the American Astronautical Society. Boy, you can't get any more brilliant speaker than Professor Rocky Kolb. Rocky, here it is.
Thank you, thank you.
You spilled my coffee, Frank.
I spilled your coffee.
Yes.
If it was floor, I don't know.
How do you turn a light off?
Simple.
No, we'll get to it.
So I've known Professor Datta, as he said, from our undergraduate days. And I believe you had a black beard, right?
Yes.
Yes. And I had hair. I had long hair, maybe to my shoulders. So we haven't changed a bit.
What about your cowboy boots?
Well, okay. So The title of the talk is Erwin Schrödinger's Alarming Phenomenon of Particle Creation in the Expanding Universe. And if there's only one thing you should take away from this talk, is that just the expansion of the universe, just the expanding universe, can lead to particle creation. So this is the outline of what I'd like to cover. I'd like to say some words about the inner space, outer space interface, talk about uncertainty in the quantum vacuum, and then how we might probe the quantum vacuum by disturbing the quantum vacuum. Then I'll have a couple of slides about the Schrödinger and his life, and leading to a look at his paper published in 1939, this alarming phenomenon paper. Then I'll talk about its relevance today, and then I'll mention exciting, imaginative new application, in other words, my work. So that's the plan of what I'd like to do. So in ways of introduction, I've spent my career working at something that I like to think of as the inner space, outer space interface, connecting particle physics and the universe. So why do this? Well, particle physics, inner space, is required to understand the universe. In the universe, there's dark matter, dark energy. There's an asymmetry between matter and antimatter, the baryon asymmetry. There's fluctuations in the temperature of the cosmic microwave background, and it's a way to understand the origin of structure in the universe. To understand these things, you have to understand particle physics. On the other hand, the universe, outer space, is a particle accelerator, and we can use it as a physics laboratory. The Big Bang, it can be used as a particle accelerator, perhaps reaching energies much in excess of what we can produce in terrestrial laboratories. We can place limits on beyond standard model physics. We can use the universe to study particles with a very long lifetime and very long path lengths across the universe. Stellar energy loss, limits on stellar energy loss can place limits on particles like axions beyond the standard model particles. And the universe has places with large magnetic fields that we'll see will play a role, or at least I'll mention it. Well, the Big Bang, the Big Bang as an accelerator assumes at some point the temperature was larger than some mass scale m. So if we want to study a particle with a mass m and use the Big Bang as an accelerator, the temperature had to be larger than m. And it's usually assumed that the particle of interest interacts with the standard model, SM, standard model plasma. But the maximum temperature of the radiation-dominated universe is something that we'll call the reheat temperature after cosmic inflation. And we don't know this value. Maybe it's 10 to the 14 GeV, or the only observational evidence is that it could be as low as 8 MeV. But gravitational particle production that I'll talk about is a non-thermal process and can produce particles with the mass much larger than the reheat temperature. Now, what about particles with no standard model interactions, or interactions too weak to be populated or produced in the primordial soup? And if we're thinking about dark matter, there's no evidence that dark matter has interactions other than gravitational interactions. Well, gravitational particle production does not require coupling to standard model particles. Another use of the inner space, outer space interface is to place limits, cosmological limits, on particle properties like neutrinos, masses of neutrinos, lifetimes of neutrinos, numbers of neutrinos. We can place limits on those from cosmology, axions, magnetic monopoles, all sorts of beyond the standard model particles, for instance, supersymmetry, cosmological defect, Kaluza-Klein modes, etc. But to do these cosmological limits, they mostly assume local thermodynamic equilibrium in the early universe. And I'll talk about how we can also use gravitational particle production to limit the properties of beyond the standard model particles. Okay, let me now talk about uncertainty in the quantum vacuum. Everyone's familiar with Heisenberg's uncertainty principle. This is a copy of his handwriting where he wrote delta P, delta Q is larger than 1/2 h bar. And I'll just take advantage of writing it as an uncertainty in energy times the uncertainty in time is larger than 1/2 h bar. One of the implications of this is that the quantum vacuum is not empty, but full of virtual particles. So the uncertainty principle implies that if we could study the vacuum with submicroscopic eyes, it wouldn't be quiescent, but it would be particles and antiparticles coming in and out of the vacuum because of Heisenberg's uncertainty principle. So the uncertainty principle implies that the vacuum is a seething sea of quantum uncertainty. Well, that's a statement. How can we test that? Well, we can disturb the vacuum. And one way to disturb the vacuum is something that's known as the Casimir effect that goes back to 1948. And the Casimir effect imagines that you have as originally proposed, two parallel conducting plates. And this would mean that very long wavelength quantum fluctuations of the electromagnetic field cannot be supported between these parallel plates. And if you can do the quantum field theory calculation and calculate the pressure, the force per area, minus h bar c pi squared over 240 a to the 4th, where a is the separation of the plates. And to give you an idea of how tricky this would be to measure, this is 1 nanonewton per nanometer squared times the separation, the inverse of the separation in nanometers to the 4th power. So to really measure this, looks like you need nanometer measurements. And what can be done is to measure force gradients. Of course, measuring a force is more difficult than measuring a force gradient. Gradients and changes are always easier to measure than the absolute value of something. And the force gradients can be measured of micronewtons per meter at separation of microns. And this is done a lot at the University of California, Riverside. And there was a recent review. Here is a reference, a brief review of some recent precision Casimir force measurements.
Do I get interrupt? I want to get hit by the ruler. So the shape of the plates matters, yeah?
Yes, the shape of the plates matter, and these measurements are not done with the plates because you just have to make them too flat to do anything. So it's a metal ball over a plate, and that so that's going to be different also. The sign of the Casimir effect also depends upon the geometry that you put there. So it's tricky things to do, but it has been measured. Here's some error bars and some models with no dissipation and with dissipation. It looks like no dissipation works. And you see the plate separation in almost goes to microns, and the Casimir force gradient is micronewtons per meter. So the Casimir effect's been experimentally determined, to me, extraordinarily hard measurements to make. All right, so putting conducting objects in the vacuum is one way to disturb the vacuum and change the uncertainty principle in these virtual particles coming in and out of the vacuum. There's another way to do it also. So another way to disturb the quantum vacuum is to turn on an electric field in the vacuum. I guess it's not a vacuum if there's an electric field in it, but turn on an electric field. So what is the electric field going to do? It's going to accelerate an electron in one direction and a positron in the other direction. And it was realized that if you have a sufficiently strong electric field, you can create particles from the vacuum. This was realized a long time ago in 1931 by Sauter, Heisenberg and his graduate student Euler wrote about this also, Vicky Weisskopf, and this is known as the Schwinger effect, proving that effects are named after the last person to write a paper about it. So Schwinger actually did the complete calculation in quantum electrodynamics. He deserves, this deserves to be named the Schwinger effect.
Let me interrupt the speaker. The speaker is Holly Compton professor in Chicago.
That's true. Thank you. So so what was realized is that you can create particles if you have the energy gained and acceleration from the electric field over a Compton wavelength of the electron in this case exceeds the particle's rest mass. What sort of electric field do we need here? What is the magnitude of the electric field required? Well, let's see what we might have. There's only one dimensionful parameter, and that's the electron mass. And then there's other parameters, the electron charge, speed of light, h bar. And what was shown is that there is a critical electric field to create particles from the vacuum that's proportional to the square of the electron mass, just on, it's the only dimensionful parameter in the problem, so it's the electron mass squared. And c cubed, 1 over h bar, and the electric charge is down here because as the electric charge becomes smaller, you need a critical electric field to accelerate them, etc. And if you put the numbers in here, the critical electric field needed is 10 to the 16 volts per centimeter. 10 to the 16 volts per centimeter. So you can do an experiment going to Kmart and buy 10 to the 16 1-volt batteries and hook them up in the basement. Well, that's not so easy to do. And, but what Schwinger showed is that this implies that the QED vacuum is unstable and has a particle production rate proportional to e to the minus e critical over e. E critical brings in a 1 over h bar, so it hints that this is a tunneling calculation, e to the minus something over h bar. Well, producing an electric field of the magnitude necessary is not possible, but there are other ways to do it. One can use high-intensity lasers. And you can guess what sort of intensity of a laser you might need, say the critical electric field squared. This turns out to be 10 to the 30 watts per square centimeter. That seems like an incredibly intense laser. But according to Nature, well, the journal Nature, they had an extreme light issue, and you can't read this, but it says physicists are planning lasers powerful enough to rip apart the fabric of space and time. Doesn't that sound violent? And ripping apart the fabric of space and time. And it impressed Ed Gerstner, whoever that is. And so Gerard Mourou won the Nobel Prize for development of high-intensity lasers. He's claimed, he said, we're going to change the index of refraction of the vacuum and produce new particles. And in his Nobel Prize lecture, I love these extrapolations. This is called the hockey stick extrapolation. He says you will reach, by 2030, reach an intensity, laser intensity large enough to have light materialization to produce electron-positron pairs just from the vacuum. I think that's pretty cool.
And the gamma rays do this notoriously all the time.
Sorry?
The 100 TeV gamma rays which we detect are doing
Well,
notoriously.
that's interesting. So, as you sort of hinted, I'm an impatient person. I don't do experiments, but I can use the universe to do my experiment. And you can realize that there are magnetic field. What kind of magnetic field you would need, just dimensional analysis, to have a critical electric field, ME squared. And this turns out to be 5 times 10 to the 9 Tesla. That is a large magnetic field. On the Earth's surface, the average is about half of a micro, 50 microteslas. So surface of the sun, 10 to the minus 4 Tesla. Sunspots have a larger magnetic field of about a Tesla. People have had MRIs. That has a magnetic field of about 3 Tesla. My friends who work at the LHC in the collider use dipoles, which have a magnetic field of 8 Tesla. The largest magnetic fields produced on Earth are produced in, anybody want to guess, where?
In Florida.
Tallahassee, Florida. Where else would you produce large
China.
They are sometimes competed by half.
Ah,
In
okay.
China, no. The recent report. China.
Okay, well,
Correct.
okay, so I'll just say 45 Tesla. Maybe it's
Plus.
45 and a half now or something.
And there is a pulse field which can reach 100 Tesla.
That's what, sorry?
Pulsed.
Pulse field can reach 100 Tesla.
It's a pulse.
per-
Wow, okay.
Explode. Well, this is-
And that's still really small.
Yeah, 10 to the 9 Tesla.
Compared to the Crab pulsar, which we're pretty sure produces a magnetic field of 3 times 10 to the 9 Tesla, and magnetars presumably have a magnetic field between 10 to the 9 and 10 to the 11 Tesla, larger than the critical value. And according to the Skeptic's Guide to the Universe, magnetars have a strong enough magnetic field, again, very violent, to rip the iron out of your blood from 1,000 miles away. So I don't guess you want to get within a thousand miles of a magnetar. You have the iron. I don't believe that's true, but anyway. I'm a skeptic about the Skeptic's Guide to the Universe. And I'll point out that there are many unexplained phenomena associated with pulsars, magnetars, etc. So perhaps something associated with the Schwinger effect is operating in the universe today, and maybe one day we'll understand it. Okay, so we can disturb the quantum vacuum by having large electric fields, and we can also disturb the quantum vacuum by having an extremely large tidal gravitational field. And again, it's the same sort of idea. In the presence of a tidal gravitational field, it's going to accelerate the virtual electrons and positrons away from each other in the vicinity of a black hole. V is equal to c at the black hole horizon, and you can have particle creation if energy gained and acceleration from gravitational field over a Compton wavelength exceeds the particle's rest mass. And this is the idea of Hawking radiation. All right, so why does a working cosmologist care about this? It's because the expanding universe can also lead to particle creation. And in a hand-waving way to see that this would happen, in the expanding vacuum of the expanding universe, there are particles and antiparticles popping in and out of the vacuum. You can have a particle and an antiparticle come out of the vacuum, get caught in the expansion of space, and if you can have, again, particle creation if the energy gained and acceleration from expansion of space over a Compton wavelength of the particle exceeds the particle's rest mass. What's the magnitude? This is not the electric field strength, it's the expansion rate of the universe, h. What sort of magnitude is required? Well, Hubble's law is that the velocity is equal to Hubble's constant times the distance. If you have v equal to 1 and distance of the inverse mass, then you might think you would need a critical expansion rate equal to the mass of the particle. So if the expansion rate exceeds the mass of the particle, you have the possibility of producing the particle merely by the expansion of the universe. And this was the idea that Schrödinger had in 1939. And now I'd like to introduce his paper, published in 1939, The Proper Vibrations of the Expanding Universe. So before digging into the paper, let me say a few words about the life of Schrödinger and what led him to the circumstances in his life to write this paper. when I was an undergraduate, Schrödinger was my hero. You know, he invented the Schrödinger equation, one of the co-developers of quantum mechanics. He loved philosophy, Eastern philosophy, biology. You know, he was just a great intellectual. But there's a saying that you should never meet your hero. Schrödinger's life had a rather distasteful side to it, and that is his relationship with women. He was a serial philanderer. What? He fooled around a lot. He had 3 children. He was married to Annie his entire life. He had 3 children, none of them with Annie. But Annie, his wife, raised his 3 children that he had with other women, and he often had living arrangements where he lived with his wife and a lover and a mistress. It's okay, so that sounds terrible, but in Zurich at the time, he was at the University of Zurich. How did Annie deal with this? Well, Annie, his wife, had a lifelong affair with Hermann Weyl, a physicist. How did Hermann Weyl's wife think about this? She had a lifelong affair with Paul Scherrer, and if you dig into what was going on at the
vacuum.
at the university, it was just crazy. But okay, so he had, and he also had a very unpleasant side that some of his lovers were quite young. Okay, so that's.
So you just made Heisenberg easy.
Yeah, right. Well, maybe Heisenberg was a Nazi, but that's.
But there's one
never
thing
mind.
wrong with that thing. That paper was produced 1 month after the Nazis invaded Poland.
Yeah, so I'm getting to that now. So this is.
The paper was published from after.
I'm probably the only one in the room that remembers that.
Ah, wow.
He must have submitted before, because the paper was published.
Yes.
After.
So anyway, I'm running through this. So in 1926, Schrödinger published a series of papers. Quantization as an eigenvalue problem. Is that the correct German translation? I think. Whoops. Uh-oh. I didn't mean to do that. Okay, I'm on the right slide. Sorry. Then after he published his papers, he went on a world tour, just like Taylor Swift. You know, you come out with an album, you go on a tour. He published a series of important papers. He went on a world tour, and he visited the U.S. He wrote that he found the noise and dirt of New York shattering. Schrödinger was a very sensitive person. He didn't like noise. When he was working, he would put in his ears 2 pearls. I guess the noise-canceling headphones weren't available to him. He would put pearls in his ear to work. You know, he just found the noise of New York shattering. He wrote that he found Chicago worse, fearing bandits who spring with loaded guns from speeding autos. Obviously, he visited the University of Chicago. His wife liked Chicago. So then in 1927, Schrödinger departed the University of Zurich for Berlin to take the recently vacated chair, the chair vacated by Max Planck. It was probably the most prestigious position for a theoretical physicist in the world, to be the professor of theoretical physics at the University of Berlin. Well, things didn't work out so well there. In 1933, the Nazis came to power, and Schrödinger had written and expressed that, you know, the Nazis were creeps, and wrote a lot of things bad about the Nazis, and he was marked by the Nazis as politically unreliable. That essentially was a death sentence. Other people marked by the Nazis as politically unreliable were assassinated, either in Germany or in other countries. So Schrödinger realized that he had to leave Berlin. So he departed Berlin for what he described as exile in Oxford. Schrödinger loved the intellectual and cultural life of Vienna, Berlin, until the Nazis came to power, Zurich, but he found Oxford rather provincial. Anybody here been to Oxford?
Yeah.
Provincial, small town.
It is provincial, in fact, yes.
He also thought people in Oxford were narrow-minded because they didn't appreciate him living in one house with a wife and a mistress and children from other women. They just thought this was strange. So he didn't like Oxford. He wasn't fond of the food either. He might eat food in England. He wasn't fond of the food. He wasn't fond of the culture. So he decided, well, I've had enough in Oxford. He won the Nobel Prize in 1933. He said, well, I can't go back to Berlin because that's too dangerous. I'll go someplace safe. I'm going to take a job in Austria. So he took a job in Graz, and he wrote that this was a miscalculation of the political situation that was an unprecedented stupidity. He didn't realize that going back to Central Europe was not a good thing to do. Well, shortly after he went back to Graz, in 1938 was the Anschluss, and Schrödinger was dismissed, but a few months after that, and he left with his wife. He left Graz for Rome with 10 marks, 3 suitcases, without the Nobel medal, and he was met in Rome by Fermi, and he took asylum in the Vatican. Now, he didn't think Oxford was a proper place to live with a wife and a mistress.
The Vatican was.
How he could have imagined that the Vatican, when you're not supposed to live with either one, would be okay. His judgment was not so great, and it's going to get worse. So he was met by Fermi in Rome, and Fermi loaned him some money. And just as a curiosity, we dug into the archives at the University of Chicago, where Fermi was a professor, and discovered a letter from a calculation that Schrödinger and Fermi did. Two of the great physicists of the 20th century did a calculation together. This is the calculation they did. Schrödinger wrote this from Dublin in 1951. He wrote, "Dear Fermi, I beg you to help me remove once and for all a remorse that I cannot help associating with my memory of you at our last meeting, namely that I still owe you 400 lira that you gave me in 1938. Then he does the calculation. To recalculate this sum to date, something like 200 Swedish crowns would be a modest estimate for repayment. If you agree, and if you still have an account in Stockholm, this would be very simple. All Nobel Prize winners should have an account in Stockholm. So Fermi wrote back to Schrödinger, always misspelling Schrödinger's name, but that's all right. He wrote, I believe you're estimating the value of 400 lira too high. At the time, the lira was worth about 1/20th, $1. So he thinks, $20 would be okay. He said, I no longer have an account in Sweden. My bank here in Chicago is the University National Bank. The bank's still there. Fermi doesn't have an account there anymore. Please, however, be sure if there are any difficulties transferring this amount, not to worry, because it's certainly not worth it. I don't know whether Schrödinger agreed with the calculation, but he agreed it's not worth it. So Fermi never got paid.
Convenient.
Very convenient. All right.
Also,
So that's
he writes, dear Fermi, not Enrique.
dear Fermi, dear Schrödinger.
Interesting.
So he realized he had to leave the Vatican. So in 1938, with France and Germany about to go to war, where does Schrödinger go? Someplace safe. Clearly, you go to Belgium. What could go wrong, right?
Of course, yes.
So he took a position
Smart
in
man.
Belgium, which I think was another stupidity. All right, so let's go back to physics, please. Thank you. So while in Belgium, he met the Big Bang cosmologist Lemaitre. And before that, in the UK, he had several interactions with Arthur Stanley Eddington. cosmologist, astrophysicist from Cambridge. And he wrote a paper in 1939 where the address is a seaside resort in Belgium. I guess this is Rabbits Lane or something like that in Belgium. July 31st in 1939, just a month before the Second World War. And in August 39, he submitted a paper, The Proper Vibrations of the Expanding Universe, that I'll talk about. And in 1956, he wrote a book, Expanding Universes. So he did have cosmological interests. He had so many different interests. So 1939, the Second World War broke out. Belgium was not a good place to be. So he deported Belgium for Dublin, where they just started the Dublin Institute for Advanced Study and built it up around Schrödinger. And he lived out the war years in Dublin and remained in Dublin until his return to Vienna in 1956, where he remained till his death in 1961. All right, so this, going back to the paper, The Proper Vibrations of the Expanding Universe, October 1939 it was published. It was received 21 August 1939, published October 1939. When Schrödinger submitted it, he was a stateless refugee, and his life was at risk. He was politically unreliable, and he was an immigrant. Terrible thing being an immigrant now, I guess. Okay, so there's no author affiliation here. So the citation history of this paper is sort of interesting. It was, first of all, never cited by Schrödinger. And for the first 20 or 30 years of its publication, it was cited 1, 2, 3 times. And it's been cited more in the last decade than it's ever been before. So it's only been cited 325 times, but most of them have been 50 years or 60 years after the publication. I think that's not the usual citation history. Okay, so let's take a look at the paper. This is the second page. You can't read this, but I can highlight something. I thought I could highlight something. All right, let me try again. Let me do this. Good. So here he writes, the decomposition of an arbitrary wave function into proper vibrations is rigorous. And by this, what I think he meant is that even in an expanding universe, a particle's wave function can be decomposed into what Schrödinger called proper vibrations, positive and negative frequency modes. So you can write the wave function in this form, and it turns out the particle occupancy number is proportional to beta squared, Bogoliubov coefficient. Then he writes, these two proper vibrations cannot be rigorously separated in the expanding universe. That means to say that if in a certain moment only one of them is present, the other can turn up in the course of time. So this means if you start with pure incoming or outgoing waves, the in and out states will become mixed in the evolution of the universe. Then he goes on to say, generally speaking, this is a phenomenon of outstanding importance. With particles, it would mean production or annihilation of matter merely by the expansion. So in 1939, Schrödinger realized that this is something of outstanding importance. The universe creates particles merely by expansion.
Do you know off the top of your head when the Russians did this?
Sorry?
Bogoliubov, do you know the comparison in dates?
Well, Bogoliubov was in the 60s.
So much later.
Yeah.
All right.
So Schrödinger's does a the guy only knew quantum mechanics. So quantum field theory, the way I understand this phenomenon, was not really developed until after the Second World War, maybe starting in 49, early 50s. So he did a quantum mechanical calculation, and it wasn't quantum field theory, and it was long before Bogolubov. So
Golubov, 1956, year before BCS paper.
yeah, okay. So, you know, if you study quantum field theory, you recognize alpha and beta Bogolubov coefficients. All right, so Schrödinger said this is outstanding importance. The universe creates particles merely by expansion. This is the last page I'll show. Just one more quote. He writes, there will thus be a mutual adulteration of positive and negative frequency terms in the course of time, giving rise to what in the introduction I called, quote, the alarming phenomenon. So Schrödinger's favorite phrase in this paper was alarming phenomena. Schrödinger was alarmed by the possibility of the creation of particles by the expansion of the universe. What alarmed Schrödinger in 1939? In 1939, he was alarmed by, in 1939, there might be creation of a single particle per Hubble time, 10 to the 10 years, per Hubble volume of 10 to the 57 cubic kilometers, with a Hubble energy of 10 to the minus 33 electron volts. So imagine in 1939, you're stateless, running for your life, sort of have a price on your head from the Nazis, you're alarmed. Somewhere in the universe, in the next 10 billion years, somewhere in the universe, a particle will appear with an energy of 10. Oh my God, this is alarming. Of all the circumstances faced by Schrödinger in 1939, this alarmed him? So it's sort of interesting to speculate why he was alarmed. Well, the appearance of particles from the vacuum sounds crazy. You know, just the expansion of the universe pops particles out of the vacuum? Sounds crazy. Now, there were technical issues with Schrödinger's calculation. He only used quantum mechanics, as I said. I don't understand how he had the insight to realize this without using quantum field theory. It's not very difficult to use quantum field theory to see this. I don't think he realized that you only create particles with mass less than the expansion rate. So today, you only create particles with mass smaller than 10 to the minus 33 electron volts. Now, what particles do we know with mass less than 10 to the minus 33 electron volts? Well, a photon, for instance. But a photon, you only create particles that violate Weyl conformal invariance. Schrödinger didn't mention this either because he didn't understand it, or he didn't like the idea that his wife was having an affair with Weyl. You know, who knows? So you don't create photons. So would Schrödinger still have been alarmed? I don't know. Schrödinger looked for and found a cosmological solution, the Milne cosmology, which is essentially just a slice of Minkowski space without mutual adulteration. Is not a very physical solution. Perhaps Schrödinger thought it was a conceptual challenge to quantum mechanics or general relativity, and I would think sometimes just follow the equations and believe what your equations tell you. I always find the equations are much smarter than I am. All right, so now on a little bit technical level, how can we understand gravitational particle production, cosmological gravitational particle production? Well, when you study quantum field theory, take a course in quantum field theory, I would bet that the course only deals in Minkowski space. Boring. Quantum field theory in Minkowski, well, it's not boring. Quantum field theory is usually taught in Minkowski space. And if you ask someone, what is a particle? Well, my definition of a particle is that it's an object described by a wave function that transforms like as an irreducible representation of the Poincare group.
Very precise.
Very precise, not understood by many people, but it's very precise. But the expanding universe is not Poincare invariant. There's a time direction associated with the expanding universe. So what a particle is a little bit fuzzy, and the notion of a particle in the expanding universe is at times approximate. All right, so here's the idea. Cosmological expansion leads to a time-dependent Hamiltonian, which will mix positive and negative frequency terms, which we interpret as particle production. All right, so here's another way to see it, a little bit more deeper than the word salad that I just gave. So imagine you have a harmonic oscillator where the frequency is a function of time. So this might be an undergraduate quantum mechanics problem. Imagine you have initial state and you solve for the wave function. Then you have a spring constant that's varied slowly, adiabatically, do a WKB, blah, 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 you know, the things you learn as an undergraduate in quantum mechanics. And if you vary the spring constant slowly enough, adiabatically enough, the wave function will respond and it will be a different wave function than the initial state. But if the spring constant is varied abruptly, non-adiabatically, then the wave function won't have the opportunity to respond to the changing potential, and the wave function will be different, and you would interpret that as an excited state, or in quantum field theory, it would be particles. Okay, so outstanding importance. Schrödinger wrote, it's a phenomenon of outstanding importance. He doesn't say why that would be of outstanding importance. And I would think that if you write a paper saying, hey, this is outstandingly important, you might want to follow it up. He never did. So the paper was forgotten in the 40s, 50s, and 60s, also by Schrödinger. And it was really rediscovered in 1966 by Lenny Parker, who was a graduate student at Harvard, a student of Sidney Coleman, and I think Sidney Coleman said, why don't you look at quantum field theory in the expanding universe? So Lenny Parker's thesis did a quantum field theory calculation, came to the same conclusion as Schrödinger. In a 1968 paper, Lenny wrote, for the early stages of a Friedmann expansion, particle creation, may well be of great cosmological significance, especially since it seems inescapable if one accepts quantum field theory and general relativity. I accept those two things. Parker did not have any speculation as to what the great cosmological significance would be. So I think people realize, hey, this could be interesting, but why is it interesting? I don't think people didn't know. So there was a lull in this interest in the 40s and 50s. In the 1960s, it was mostly regarded as a curiosity. People in the US, Soviet Union, some in the UK worked on this. The great cosmological significance of particle creation in the expanding universe was not realized until the 1980s within the context of cosmic inflation. And there's a long list of names I could give. Slava Mukhanov is often present when I give this talk, and if I don't have his name first, he always yells at me. So in case he's watching online or something, well, Slava played a big role in this.
He may yell, but what he did, it was 10 or 11 or 15 years after Zoldovich and Starobinsky.
Yes.
You can yell.
Well, Zoldovich and... okay, so the great cosmological significance, Zoldovich had an idea for the great cosmological significance. He thought that you could start with an inhomogeneous anisotropic universe, and particle creation would lead to isotropy and homogeneity. And Starobinsky worked on this with him, and that never worked. So we understand why the universe is homogeneous and isotropic. Today we understand it because of inflation.
Yeah, Harter worked on this too, Misner and others.
Yeah, okay, good. All right, so I have two sort of quantum field theory slides, so just stick with me for 2 slides and then the equations will go away. So let's consider a scalar field in a Friedmann-Robertson-Walker background. What would you do if you're assigned this problem? You would write the covariant action for a scalar field phi. There's an invariant volume, the Einstein-Hilbert action, the kinetic term involving the metric tensor, and a potential term. Let's just take it simple, quadratic potential, and you can add a non-minimal coupling proportional to some unknown parameter c and the Ricci scalar. So this is where gravity enters the picture. So to do quantum field theory with this, you're going to go 2 steps. One, I'm going to consider this in a spatially flat Friedmann-Robertson-Walker background with the metric in conformal time eta written in this form. So I will always be working in conformal time. Cosmologists work in conformal time. I have an app. My watch keeps conformal time, not Eastern time, Central. I keep conformal standard time on my watch. So this looks fine, except the kinetic term is not a canonical kinetic term. So we want to do quantization, understand the dynamics. We have to have a canonical kinetic term. So there's a field rescaling, and you end up with an action that looks for the scalar, this rescaled scalar field that has a kinetic term and a potential term. And the thing that's interesting about it is that the effective mass is time dependent, depends upon the evolution of the scale factor of the universe as the universe expands. And if it's not conformally coupled, if c is not equal to 1/6, it also depends upon the Ricci scalar in the expansion of the universe. So I'll just mention, I'll mention later the effect of these non-minimal terms for the scalar field. There is a term proportional to some coupling constant c. If c is equal to 0, it's known as minimal coupling. You just ignore that term. If c equal to 1/6, there's an additional classical symmetry to the action, conformal symmetry. So, but in general, I think from the modern effective view of effective field theory, c should be a free parameter. C equal to 1/6 is an enhanced classical conformal symmetry point, but it's classical, and quantum effects will break the symmetry. But why not other non-minimal terms? Well, this is the only dimension 4 operator involving the Ricci scalar, Ricci tensor, and Riemann tensor that one could add. And no symmetry forbids it. From the effective field theory point of view, it should include it. Furthermore, C should not really be a constant. There should be a renormalization group equation for the evolution of C.
Actually, in regards to that, and in another attempt to get hit, I thought for renormalization, C has to be 1/6. Is that an old argument, or do you have anything to say about it?
1/6 is classically, no, I don't think 1/6 is a stable point in the renormalization group.
Okay.
This is a point where there's no renormalization of Newton constant.
Yes, right.
That's basically
That's true. Let's keep it simple. All right, so let me talk about inflation. The usual picture of inflation is the universe is dominated by the potential energy of a scalar field. We don't know the nature of this scalar field driving inflation, but we have a cool name for it, the inflaton. And if you have a cool name for something, that counts. So the scalar field has potential energy, V, and kinetic energy, phi dot. So you have some field and a potential, and the potential energy during inflation, which is the zero momentum mode of the scalar field, dominates. And if this dominates, it leads to an acceleration of the universe, or what we call inflation. So the inflaton field drives inflation, But in the expanding universe, Schrödinger's alarming phenomenon occurs, and you will create the inflaton field just due to the expansion of space. If particle creation, etc., acceleration, expansion of space over comping with blah, blah, blah. So Schrödinger's alarming phenomenon applies to the inflaton field, and the inflaton field, it would be the Mukhanov-Sasaki equation that you would solve. Okay, so what are the implications of this? So the Schrödinger's alarming phenomenon produces inflaton particles. Particles will be produced with non-zero momentum. With non-zero momentum is finite length scales. So there will be production of inflaton particles which lead to perturbations, spatial perturbations in the inflaton field. The inflaton field dominates the energy density, leads to spatial fluctuations in the energy density, which will also lead to spatial fluctuations in the temperature. The particles are produced when they cross the Hubble radius during inflation, and generally, approximately, this produces fluctuations on all scales with approximately the same amplitude. This is known as the Harrison-Zeldovich spectrum, named after Yakov Zeldovich and George. Students, do you recognize this photo? No, students. George Harrison. There used to be a band called the Beatles. Anybody remember? Anybody ever? No, nobody's heard of the Beatles. Okay.
This is not Ed. This is not Ed Harrison.
No, yes, it's Ed Harrison, of course.
Way to catch up.
Oh, of course I caught that. Of course.
I couldn't find a picture of Ed,
Oh.
but there were a lot of pictures of George Harrison.
Yeah. Ed was a very modest guy.
Yeah. Okay, so here's the idea. For the microwave background radiation, Schrödinger's alarming phenomena leads to quantum fluctuations in the temperature of the microwave background radiation. So if you look up at a city, I think this is Columbia, right? No, it's Chicago. So if you look up in the sky at Chicago with eyes sensitive to microwave radiation, very sensitive to temperature fluctuations in the microwave background radiation, what you would see is not uniform temperature, but a pattern of temperature fluctuations which reflect a pattern of vacuum quantum fluctuations. These are fluctuations in the vacuum that once started 10 to the minus very large number centimeters, and the expansion of the universe have stretched these fluctuations to be as large as the observable universe. So you're looking at a pattern of vacuum quantum fluctuations when you look at fluctuations in the microwave background. Now, if you would say h bar is equal to 0, if you would ignore quantum mechanics, which I don't recommend you do, you wouldn't see the vacuum fluctuations. The temperature would be exactly uniform. And what about the density? So we look out this is with my backyard telescope. I look out at the universe and see structure in the universe. Now, where does the structure come from? The structure also comes from Schrödinger's alarming phenomenon. So if I would take h bar to 0, ignore quantum mechanics, there wouldn't be structure in the universe. There wouldn't be galaxies, stars, planets, people, poodles. They just wouldn't be around in the universe. So here's something to make you feel good. You are the result of quantum uncertainty in virtual particles. You are an amplified quantum fluctuation. Yes. All right, so quantum fluctuations, once microscopic, have been stretched to be as large as the observable universe. And the map of CMB delta T over T is a map of quantum fluctuations, perhaps produced 10 to the minus 35 seconds after the bang during primordial inflation when the universe was dominated by vacuum energy, and rapid expansion ripped particles out of a quantum vacuum, Schrödinger's alarming phenomenon, producing the primordial seeds of structure that grew to all we see. You are in amplified quantum fluctuations. And encoded in this pattern of quantum fluctuations, pattern of CMB fluctuations, is the imprint of fundamental physics during inflation. But wait, there's more. Act now. So the expansion of the universe also will produce gravitational field. The expansion of space will produce the gravitational field. So it's the same idea. So today, Big Bang plus 14 billion years, we look out in space back in time at the microwave background radiation, and this pattern of fluctuations reflects what went on during inflation, perhaps Big Bang plus 10 to the minus 35 seconds. And we can see density, temperature fluctuations, deduce density fluctuations, and there's a very large activity looking for gravitational waves. Yes?
Can I ask a quick question here? In Astronomy 101, we say we also introduce these fluctuations as a result of dark matter clumping. Is this an alternate view of the creation of fluctuations? They both exist?
So the technical calculation would be you produce curvature fluctuations. Yeah. And the curvature fluctuations cause fluctuations in the baryon density and the dark matter density. And so there's another step. So it's not wrong to say the fluctuations are dark matter, but it's also fluctuations in the baryon density. And technically, it's fluctuations in the curvature.
Gotcha.
And these guys like to oscillate. So they produce Sakharov peaks.
So don't change anything that you teach. Maybe not talk about curvature fluctuation. All right, so could there be more? This is sort of a cool idea. Gravitational particle production is universal. It's not a large effect. The CMB perturbations of order 10 to the minus 5. What else could be observable? Dark matter, isocurvature perturbations in the CMB, non-Gaussianity in the CMB, and maybe a baryon asymmetry. And I've worked and am working on all of these aspects. So let me just say a word about dark matter. Every cosmologist is required to show a slide like this, the pizza graph of the present composition of the universe. The early universe was radiation dominated, but today, most of the radiation in the universe is in the microwave region. In terms of the total mass energy density, it's only 0.005%. This also shows why chemistry is not important. The chemical elements, by which I mean elements other than hydrogen and helium, is only 0.025% of the mass and energy of the universe. Before I became dean, I didn't understand why we had a chemistry department. Why do we have to have chemists? It's such a small fraction of the mass and energy of the universe. But I was convinced that every university should have one chemist. So. All right, so
I hope none of them are sitting in here.
I love chemists. Neutrinos, much larger fraction of the mass and energy than chemistry. Stars, hydrogen, helium, most of it's dark matter and dark energy. I don't have a clue what the hell dark energy is, but maybe dark matter is something interesting. So I'll just mention this. For at least 40 years, the leading dark matter candidate has been a weak scale cold thermal relic with a mass in GeV to TeV and weak scale interactions with the standard model produced by freeze out from the primordial plasma. And the great thing about this is theorists are very mean. They can they can convince experimentalists to spend 40 years of their life looking for this. They're very naive. You know, you just tell them, go off and spend 40 years.
Are you looking at me?
Yeah, I'm looking at you. Maybe detectable by direct detection. But WIMPs and supersymmetry have stubbornly evaded detection, so perhaps it can be produced by gravitational particle production. So I'm out of time. What sort of mass would the dark matter have if it's produced during inflation by Schrödinger's alarming phenomenon? It would have a mass, very large mass, 10 to the 12 to 10 to the 14 GeV. And this is known, this very large mass is not a WIMP, it's a WIMPzilla. It's a very large, massive WIMP. And I think we should be friends with WIMPzilla. So here's a WIMPzilla, here's me sitting looking at Chicago. WIMPzillas are nice. So that's my idea, that dark matter is produced by Schrödinger's alarming phenomenon. I have many more slides to show about this, but I see I'm out of time. I've been working on this since 1998. Here are my collaborators that I've worked on with this. It's a long list. I've been spending 25 years of my life working on this. Okay, so I'm out of time, so let me just skip to the end. So this is what I've been working on, the idea that you start input cosmic inflation, quantum field theory, and general relativity, and the properties of some particles, and use cosmological gravitational particle production to produce primordial gravitational waves, which may be detectable, primordial curvature fluctuations, which have been detectable, perhaps dark matter populating hidden sectors, C and B isocurvature fluctuations, using it as a probe of beyond the standard model physics, producing the baryon asymmetry. It's, to me, the alarming phenomenon that keeps on giving. So I'm out of time. I'll stop there, and thank you very much. Again, the takeaway is that the expansion of the universe creates particles from the vacuum. Thank you.
So who created the vacuum?
Who created the vacuum? Well, you know, the vacuum is more than nothing. Nothing is something. That's something to remember. And it's Heisenberg's fault of quantum uncertainty.
Frank? You remember back when they made the first measurements of the microwave background fluctuations? Right on the front page of every magazine was, you need to go and find the dark matter. Make that connection, because it's right up your alley.
Yeah, so I think there are sort of a lot of cosmological questions. One of the nice things about being a cosmologist, I am a cosmologist and proud of it. You know, every April 15th, when I fill in this little form asking for my occupation, I write cosmologist. I think they look at it and say, this guy doesn't know how to spell cosmetologist. But I explain cosmology is the makeup of the universe. Cosmetology is a universe of makeup. That, you know, there's a lot of jokes I have there. I'm sorry. What was the question? Oh, yeah. So the nice thing about being a cosmologist is some of the questions you try to answer are simple to state. The answers aren't so simple, but the questions are simple to state. Now, if you're working on neutrino physics and you tell people I'm trying to decide whether it's a normal hierarchy or an inverted hierarchy, that it's not so easy to get across. One of the simple questions is, what is the universe made of? You know, what is most of the matter in the universe? We don't know. We have a name for it, dark matter, but naming is not explaining. We want to understand the nature of dark matter, and it's something that's driven a lot of my research, coming up with models for dark matter. And it's some of my poor experimental friends spend their life looking for dark matter.
Nice occupation.
Without finding it, right. So, you know, I'm a theorist. On a good day, I can come up with 3 dark matter candidates before breakfast. And experimentalists might spend 20 years of their life proving I'm wrong. So they come back and say, aha, you're wrong. I said, well, I have more candidates, you know, I did.
David.
In particle physics, when we do, say, pair production, you know, from photon oscillations to produce E plus E minus pair, we need a nucleus to have some recoil momentum, put those particles on shell,
Yes.
make them real. What happens here? The vacuum expanding creates the particles. Are they virtual, and do they affect where the vacuum itself?
It turns virtual particles into real particles.
They get the kick.
A very small
So they get the kick. So does that affect the you know, the vacuum
So-
itself? Does it carry some recoil or something? I mean, how does that?
So is there a back reaction on the energy of the vacuum? And this is a question we argue about. I don't think so, but some of my friends who are very smart and wrong think that it does.
Very smart.
Thank you.
Rosenfeld.
So, I think about neutrinos some, and when you show the virtual particles in the vacuum, it seems to me that the neutrinos have a different cross-section on the one half than the other because they're sensitive to particle-antiparticle. So can we see a difference in neutrino oscillations as they propagate through vacuum?
Well, you would
Between
have to do the
neutrinos and antineutrinos.
you would have to do a calculations seeing whether the energies are able to accelerate the particle to relativistic speeds over a Compton wavelength of the particle. So I'm not sure I understood your question.
Well,
I gave an answer, but it's not to the question
but
you
I would only
asked.
say, why do they have to do that acceleration? Why can't we have recombination and never see the real particles evolving from that?
Well, we don't see real particles evolving from the vacuum because we don't produce an electric field large enough to produce it, or a magnetic field.
If light propagates through glass, it has an index, and we don't see excitations in the glass.
Well, we don't excite particles in the glass to relativistic speeds over a Compton wavelength of the particle.
Of course we do. You have photons. Light scatters with the
Okay,
something which
let's have the
vibrates.
conversations
That's what
later.
I'm saying.
We have other questions. So, Milind?
Yeah, I'm trying to ask something similar to what David asked earlier. So my idea was that up to whatever that time is called, 380,000 years, there was this interplay between photons and baryons, and he says dark matter, so fine. And that's the earliest we can go to from these.
Directly.
But now you're saying it's the curvature far before that. And so how do you know that these things they had 380K years to interact, right? So,
Well, no is a word I'm reluctant to use. So I think as scientists, 2 words you should never use is no and believe. You know, belief is some other field, theology department, not the physics department. So the idea is that the fluctuations in the microwave background radiation have an imprint of events that happened much earlier. So an example, an analogy I could use is, suppose you go to a telescope and look at a moon of Saturn, Tethys, you see all sorts of craters on it. So you're observing the surface of this moon as it existed 10 hours ago, because 10 hours, I think
Light
10
hours.
hours is a light travel time. But in the imperfections on the surface, there's a history of the cratering over the entire history of the solar system. So the imperfections lead to knowledge that you can get over the history of the solar system, not just at the time you're observing it, but over the integrated age of the solar system.
yeah, but I have this idea that before 380K years, the universe was a very dynamic place, unlike the craters of Tethys.
Well, the early solar system was pretty dynamic also. You know, if you were a dinosaur, you, you suffered from the dynamism of the early solar system. And just because something is far away, either in space and time, doesn't mean that you can't understand it. So I can predict the temperature on the surface of Mars 3 weeks from now with much more accuracy than I can predict what the surface temperature of Columbia will be 3 weeks from now. It's much farther away, but the physics is simpler. There's no atmosphere and things like that. So just because something's far away and a long time ago doesn't mean you can't say something sensible about it if you understand the physics that's going on. So we try to apply the physics that we understand from the laboratory, apply it to the universe, and see where it will take us. So inflation may be wrong, and the way to show that it's wrong is to come up with a better idea.
Varsha and Enrique. Varsha.
So, for observers of the distant universe, what more future experiments would you suggest making, either for the CMB itself or distant high redshift galaxies or
Yes.
anything?
Yeah. So what I would like observers to do is to look hard at the microwave background radiation and see if you can detect the imprint of gravitational waves. That would give us information about what happened during inflation. It would tell us what the expansion, directly what the expansion rate during inflation would be. So that's the one thing I would like to get. Another thing I would like to get is my experimental colleagues to discover what dark matter is. That would be really good. And observers who do modern astronomy observations, there are some hints that the standard cosmology might be incomplete, going from the time of microwave background radiation till today. This goes by the name of the Hubble tension, the sigma 8 tension, and but the trouble is astronomy is hard. It's really hard. And the systematic errors will turn around to bite you. So people say, I see some indication that the standard cosmology is wrong at 5 sigma. Well, that's the statistical error, but the systematic error in astronomy is much harder to quantify. So we'll see. Keep doing what you're doing.
Yeah. So some radio-loud anti-galactic nuclei, so that, you know, they have the jets with a magnetic field electrical, so that implies that you have a inward electric current, and that electric current has a power of more than 10 to the 30 watts. So
right. Okay.
It's very interesting that you say that, because you can have this electric current in the radio
Wow.
jets.
Okay. I didn't know that.
AGN.
So you think magnetic fields might be interesting?
Yes, so yeah, in my case, yes. But yeah, so then like I try to put myself on as a grad student, and then on this yellow sentence that you have here, and you have to create a vacuum. So I'm thinking about like what happened with the conservation of energy.
Oh, great, good.
So what happened with energy, and how do we conserve the? So you created something from nothing.
Yeah, that was my question.
Nothing is something. There's quantum fluctuations in the vacuum. Nothing is something.
So then that's implicitly imply that you are putting some energy into the vacuum.
Oh,
so
pulling
then
it
the vacuum
out.
has
Yeah.
some energy itself.
Well, that goes back to the question, is there a back reaction? And I don't think so, but I don't think that's a settled issue.
Is the pumping